final topic in this set of lectures, which will be we once again try to make contact with experiments, but now instead of phase-space integrated observables, we look at it via phase-space differential observables. And here we saw once you integrate over phase space, you are only kind of limited to the freeze out stage, right? And you cannot look at any earlier stage. Mm, the earlier stage physics is almost invisible to you because you are already in a framework where you are assuming complete equilibrium, thermal and chemical equilibrium, and so the history is lost, right? Um, but is that all that we can hope to learn from heavy ion collision experiments? Well, certainly no. Once you start looking at the details of the phase space occupation of the hadrons, then what we will see today that to understand the phase space occupation of the hadrons, one needs to basically have a good model of the fireball initial condition, how in what kind of properties the fireball is formed with, and then the fireball's evolution till the freeze out, right? So in that sense, these phase space differential observables, they allow you, right, to look uh, um, beyond freeze out, right? The freeze out is almost like an iron curtain, but these phase space differential observables indeed help you to look beyond it, right? Which is good because then we can learn many things about the QGP state and also QCD in these extreme conditions. So from the initial condition and so on, right? So this is what we will try to discuss today. So contact with experiments via phase-space differential observables. Okay, so the first question, I mean, the first topic let's put up. So static versus expanding medium, right? Whatever discussion we have done so far, right, in the framework of lattice QCD or say hadron resonance gas, we have been, I mean, silently assuming this thing, right? That it's a static medium. It's just a QCD medium, which is just sitting quietly, and in some way we can change its temperature or vary on chemical potential. And so in those different thermodynamic state, what kind of phase in which that medium will be, right? That has been mainly the question. So the hadron resonance gas or the lattice QCD, this represents a static medium in complete thermal and chemical equilibrium. Okay, and then we try to make contact with the freeze out. So what it is basic, so the picture that we kind of drew in our mind yesterday was that at freeze out we seem to have a medium which is in complete thermal and chemical equilibrium, right? Like a static medium. Because you see, let's refer, for example, in HRG, this formula we had come across yesterday. So, for example, the number density is like this, right? So, so what is this telling you? It's just a thermal gas which is static, right? There is no expansion or no flow or anything, right? It's just a hot and dense thermal gas, right? Or a medium. So what you see over here that the the px, py, pz, right? They actually always appear in the form of p square, right? So what does that mean? That your x, y, z, all these are equivalent, right? Because in E also you will have p square, and here also you have p square. So all, as a result, all directions are equivalent. And if you say, okay, but you are putting a cut, so this this verification is only at, strictly speaking, only at mid-rapidity region, we can take that point granted. So then at least what we can say that at mid-rapidity, at least the transverse directions are all equivalent. So let's say X and Y, these are all equivalent, right? So this is the picture we kind of, formulated when we saw such good agreement between HRG and the yields, and we established the freeze, right? So, but then if you just have that picture, okay, then there can be, it could be misleading, right? So why is the topic of today's lecture, and the argument starts in the following way, that the momentum space occupation, right? Here, when we do this analysis, we have integrated out the momentum space details, right? So all those information are gone, and then we drew this picture. But if you decide not to integrate out the momentum space information, because in experiment you do have that information, right? That at a px, at a py, okay, at a pz, well, what is the number of particle? You have that information. So if you now work, if you now want to understand, I mean, work with that information, with this differential information, then what do we see? So the momentum space occupation of the emerging hadrons, right? I hope this thing is clear what I mean by this, right? I exactly mean this, right? At different phase space or at different momentum space, how many hadrons are there, right? So this is like a phase space differential information, right? Or a momentum space differential information. Unlike in this yield, where we had already integrated the total momentum space, and then we started talking about theory versus experiment. So if you don't integrate it out, if you want to look at the momentum space occupation of these emerging hadrons from the fireball, right, at the time of freeze out, remember, I mean, when you are getting the hadrons in the detector, right, the last time, if the firewall is somewhere here, we can think, and so they're all coming out. So the in the detector, the information that you are measuring, okay, if assuming that the hadrons had only free streamed, right, from the firewall to the detector, that means whatever was their state at the surface of last scattering or at freeze out, right, that state do not change, and they come with that same momentum and register at the detector. That means what you are measuring in the detector is the state of the hadron at the time of freeze out, right? So the momentum space occupation of the emerging hadrons from the fireball at the time of freeze out, okay? So if you want to study this momentum space occupation, one thing that you could do may be studied by a suitable Fourier decomposition, right? For example, you want to understand if there is any difference between x and y, say, right? Suppose we are at mid rapidity, so we have this transverse plane, right? X and y, right? And there are these different momentum, right, with different components of px and py, right? You want to study that this distribution. One thing, for example, you could study is what is this azimuthal, what is the dependence on this azimuthal angle phi, right? So for that, you could expand that dependence in a Fourier series expansion, right? Cosine and sine series, right? And this is what is commonly done. So you measure this in a given PT Y phi bin, how many hadrons are there, and then you try to expand, keeping the same PT and Y. Let's say we expand in the Fourier series in the phi. So basically we want to look at the the azimuthal dependence, right? The azimuthal dependence. So when you do that, you are having these different expansion coefficients, Fourier expansion coefficients, VNs, right? And they characterize your this azimuthal dependence, right? So in the most general case, you will have this coefficient as well as these angles, the psi n's. Okay, so I will come to precisely this Vn and psi n a little later. For now, let's just focus on the fact that you have these coefficients. I mean, you could have. So the reason that here there are two constants that are coming. Usually, you when you write a Fourier series, you will write like summation n a n cos n phi plus bn sin n phi maybe, right? Here we are putting all this together, right, like a cos thing, but you can clearly see that we are not losing out. Here also there are two undetermined constants, ans and bns. Here also we have the vns and the psi-ns. Okay, these two are indeed equivalent, right? Because you can expand this cosine phi minus psi. You will get a cos phi term, you will get a sine phi term, and that will be precisely these two terms. Okay, so they are same. Don't get confused. It's just a nice way to write in this way, but I mean, you could also write in this way. In fact, in literature, sometimes you will also see this kind of an expansion. Okay, right. So this is the most general. So you can always expand this, and then you can try to see what are these VNs or sign. For example, if you want to look at this VN, right? So you can write from this expansion what will be this VN at a given PT and given Y, right? So all you have to do, you have to just take the average of this the corresponding n, the corresponding cosine n phi minus here. If I take this expansion, this instead of phi r, I should be having a psi n, right? So cosine n phi minus psi n, and its average, this angular bracket. By the angular bracket, what we mean is basically this, right? So you are integrating over all phi um, with the weight factor, which is the spectra or the number of hadrons you have at that phi. And with that weight factor, you are trying to compute the expectation value of this quantity, cosine n phi minus psi n. Okay. And then you normalize again with the weight factor to get the average value. So, so what does this tell you, right? If you have this kind of a scenario, right, just a static thermal gas, then it should not have any azimuthal dependence, right? It's a completely thermal equilibrated thermal and gas in thermal and chemical equilibrium. It has no preferred direction or anything, right? So hence you see here x and y are equivalent. So all such um, expansion coefficients, these should give you zero, right? Because it is independent. It does not depend on phi, right? It is independent of any azimuthal dependence, right? So if it is indeed uh, this kind of a medium at freeze out, then we should get zero VNs, right? And if it is not like this, right? If it has some preferred directions, how that preferred direction can come, that's then a very important question. Because why should a collision suddenly pick out a preferred direction, right? So, but if it is there, then it should be non-zero, right? So that's just, in one case I'm saying it's like just a static gas, right? Thermal, in complete thermal and chemical equilibrium, it has no direction, nothing. So that is this scenario. If then the flow coefficients should be zero, right? And the other thing is, okay, this is Vn non-zero, okay? And what we will see, to understand this, then you have to view it like an expanding medium with a very appropriately chosen initial condition to explain all these things. Okay, So that is the things that are coming up. Okay. So now the question is, what is Vn actually? It can be measured, so it has been measured, and here what I show is the particular value for n equal to 2, right? V2. This is at 200 GeV gold collisions, okay, at RIC. And what you have here is the transverse momentum PT, okay, and the second Fourier harmonic coefficient. And here are data from the STAR and the Phoenix experiments, and we have data for different hadrons. Also, we have some model calculations from a hydrodynamic framework, which are these lines. Now, in this course, we won't focus on this model calculation. However, we in this school we do have a dedicated, I think, two-lecture course by Victor, where he will be explaining these model framework in details. But for now, I just want you to focus on the symbols, right, which is the data. Okay, and so what it is telling that indeed this V2 is non-zero. Okay, so which means that this picture, the picture that we drew for ourselves yesterday, okay, is of course there is some truth in it, but it's not the full truth, right? It's not just a static gas in thermal and chemical equilibrium, because if it was so, then in no way it can have such angular dependence and so on, right? There is something more to it. And so non-zero second harmonic flow coefficient and at freeze out, okay, as I explained here, right? Everything that you're observing, it is coming from that freeze out, at least these strongly interacting probes, okay? And the phase-space differential observable. So this is the main point that I wanted to convey, that the once you start looking at such phase-space differential observables like flow here, V2, okay, like this. So the phase-space differential observable like the second harmonic flow coefficient, it reveals that the medium at freeze out has more features than just being in thermal and chemical equilibrium. That's what I've been trying to tell you. Right? So, so it has more features, right? Means it has these non-zero flow coefficients. So what does that mean, right? Non-zero flow coefficient at freeze out, right, reveal breaking of azimuthal symmetry, right, in the transverse plane. Okay. Now, such breaking of azimuthal symmetry, okay, you might ponder what is the source of this azimuthal dependence, right? So such dependency on the azimuthal angle, if at all, has come in, it the only possible way it can come in is that it has to be in the initial condition itself, right? The way the fireball is being created, because between the initial condition and in the freeze out, right, it is just an expansion, right? And the expansion by itself cannot break this symmetry, right? Azimuthal symmetry and so on. So if in the freeze out here, we see that there is a phi dependence, okay? That dependence must have come from the initial condition itself, okay? So, so then what becomes important in this game is to understand these observables in the model. One has to now then worry about or understand what sort of initial condition should be valid in these kind of collisions. What should be the initial geometry? For example, here we are talking of phi dependence geometrical feature. So the what should be the initial geometry that one should take into account in such collisions, right? So that's how you see the moment you go from phase space integrated observable to a phase space differential observable, right? Your scope now goes beyond the freeze out and you start being sensitive to what kind of modeling you are doing, even at the initial condition level, right? So, so the initial geometry, the initial relevant geometry, which could be coming from just the fact that you're colliding two nuclei, right?
Sandeep, can I?
Yeah. Uh,
Can I ask a question? So this is Devashish.
Hi, Devashish. Yeah, tell.
So on the previous slide, so one question. So this initial anisotropy, can they be that signal be washed out if we allow, let us say, a lot time for the system to evolve and then interact, the particles interact?
Yeah. Yes, that is possible, right? So of course, I mean that's what equilibration always tries to do, right? It tries to wash out history, right? So initial condition is also like now a history, and this expansion and the medium response is such that it will always try to wash this out. So for example, there will be dissipative processes, okay, ongoing dissipative processes in the medium, and if they are of considerable magnitude, okay,
Mhm.
they could wash out all such initial condition features, and in the end then you would just get a like a thermal, completely thermal and chemical equivalent, just a thermal gas, and you would not be then seeing these flow coefficient or such. You would get the all of these to be zero.
So
If
a
you,
thermal equilibrium can lead to this isotropation. And okay.
yeah,
So what we are seeing in the experiment is we still see V2. So that does that mean like it is due to a short lifetime and short size that constrains those initial anisotropy not to wash away or something like that?
yeah. So there are various factors. So if you have to understand that, then one has to enter the details of the hydrodynamic. For example, a particular evolution model, right? And one of the, I mean, best candidate is a hydrodynamic model, mainly because most of the things that are the ingredients in this model are under control, right? Um, for example, there are very few parameters, right? So now those parameters, for example, the viscosities, right, the transport coefficients, right? So what it means is those transport coefficients are of a certain value, are in the range, right, of certain value range, such that, I mean, you are able to see these flow coefficients even at freeze out, right? If those
Okay, okay.
transport coefficients were very large, then it would have been possible that there was a lot of transport and dissipation, and very soon all these anisotropies are washed out, and maybe the
Okay,
firewall
nice.
is still not frozen out, so it could be still expanding and it freezes out after some more time, and so by that time all the vns have sufficiently gone down to zero. Okay.
It also depends on the medium property like eta base, right?
Yeah,
Okay, okay.
yeah, it very much, yes, it very
Yeah,
much,
yeah.
and hence this is a very sensitive probe, right, to initial
Yes.
condition as well as the medium property that you are assuming.
Okay. Thank you. Thank you, Sandeep.
Yeah. So in fact, I mean, we have. I mean, in the next slide, we will come to a higher transport. I mean, higher flow coefficient. Like this one is V2, this is V3, and this is V4. So you see already V4 has gone down sufficiently. Uh, it has gone down, right? So and this has gone down mainly because of transport coefficient. Okay. Uh,
Oh,
so the role of this transport coefficient is indeed to kill these anisotropy and all, and make it look like as much possible as the highest entropy state, so complete global equilibrium kind of thing. So then you have no, I mean, the only thing you can extract is a temperature and chemical potential and nothing else. All the history is gone. That always, this is the role of dissipation.
So
Okay.
that property small eta base also helps us, right, to
Yeah.
get
Yeah.
this
Yeah.
initial.
Yeah.
Okay,
Yeah.
okay.
Yeah. So it just happens that QCD has this kind of a range, and also the lifetime is appropriate. So all those things fall together to give us this kind of values, right?
Okay, thank you.
Okay, good. Okay, so right. So in order to understand this, we need to understand how this symmetry is broken in the initial condition. Um, and so the first thing is, just from the fact that you are colliding two nuclei, um, right? What sort of geometry one could expect? So the nuclei here are being represented by these circles. So this is like a transverse cross section, and so the overlap region is what you get like an ellipse, right? And so once you have this, automatically you see there is a phi dependence. There is this azimuthal dependence that you can put in your initial condition, right? So this is what is known as like a geometric origin to the flow, particularly to the second Fourier harmonic coefficient, which is the v2. So this is a geometric origin to v2, right? Of course, this is a special case. So this x and y is of course your definition, which we say like the lab frame, right? That is your choice. The nuclei now collides. Now this is a very special picture where the nuclei are also colliding such that the minor axis of this ellipse is aligned with your lab frame. This will of course not happen in general. What will happen in general is this, right? Where the minor axis of this ellipse will be aligned or oriented with respect to your lab frame at a certain angle, which we are denoting here like this phi r, right? So which is known as this reaction plane. So this is the orientation of the reaction plane in the lab. So now the interesting thing is, once you if you have just this picture, note one thing, that then the Fourier expansion, if you do, the azimuthal dependence that you would expect, okay, is of this type. You have the Vn, but now you just have phi minus psi r, okay? So this is phi r, sorry, and this phi r is constant, right? It is in the initial condition itself. It doesn't depend on n, unlike the most general expansion that we wrote here, where this was psi n, right? And this we said is equivalent to the most general Fourier expansion, where you have both cosine n phi as well as sine n phi. Okay, but here, okay, we are just keeping the cosine terms and not taking into account the sine terms, and that is because you see, by by representing the nucleus with just these circles, right? So this is a AA type of collision that we have taken here. Is there a question? Okay. So this is a nucleus-nucleus collision. It's a symmetric collision, right? For example, gold-gold or lead-lead. So what you see, there is a symmetry for phi minus phi r, okay, going to phi minus phi r plus phi, right? So all I'm saying is, if you kind of flip this, if you make this as projectile and this as target, right? Nothing changes, right? I mean, in this picture here, it's very easy. You can just imagine, right? So if you take a phi to phi plus pi, or here phi minus phi r to phi minus phi r plus pi, nothing changes, right? There is symmetry. So then what you expect is that from here, that only n even even n's will contribute, okay? Because the if it is a odd n, okay, then you have uh, when you take phi minus phi r to phi minus phi r plus pi. So if it is a odd, suppose you are multiplying with 3, okay, then you are also putting here 3 pi. So that's a minus sign, right? Minus, it will just become cosine of that, will just become minus of cosine of 3 phi minus phi r. And so once you integrate that over all phi, it will just give you 0. So all the odd harmonics will drop down, right? So this again, then you can ask, are you seeing higher harmonics? I mean, you see non-zero flow coefficient, that is okay. Okay, that says, okay, there is some, in the initial condition, there is symmetry breaking. But now you ask, do you also see um, non-zero odd harmonics? Okay, because if it is this kind of thing, the prediction, a very strong prediction is you should see zero odd harmonics, right? And then so this again you can go back and measure, and what we have seen is that there is sizable, okay, odd harmonic flow, v3 for example. So it can be smaller than v2, but it is definitely not zero. It is significantly away from zero, and one has to accommodate this. So if you now start with the initial condition of this type, no way are you going to get that non-zero v3, okay? So you need to break the phi minus phi r to phi minus phi r plus pi symmetry in the initial geometry. So here we had considered the nucleus. So what then people thought, let's go from just the nucleus to let's consider the nucleus together with the fact that the nucleus is nothing but, I mean, collection of these nucleons, okay? So then the picture now you have to imagine in your head are that instead of this circle, okay, you have to think of it like a bunch of these nucleons, right? So once that happens now, the symmetry of a perfect circle is gone, right? Now I cannot say that if I interchange my target and projectile, nothing changes, right? Because even if both are say gold, okay, this gold is slightly different from this gold, right? Because we are talking of a particular collision in which this gold, the nucleons are distributed in a certain fashion, okay? And in that same time, the gold with which it is colliding, in that gold, the nucleons could be distributed in some other fashion. So each realization of this gold nucleus at the time of collision is some unique uh, configuration of nucleons, okay? So that now, so even though it is a symmetric collision, a collision, okay, but really if you think like event by event, it's some a plus b collision, right? When you try to think in terms of the fact that it's a collision between the nucleons, right? Because the position of these nucleons could be different. Of course, there are more sources. Okay, inside the nucleon, now if you think how the quarks and gluons are distributed, okay, so that could also be different in different nucleon, and so those are, uh, I mean, you could keep on adding such fluctuations, and there are improving step by step. You can have more and more refined initial condition model which tries to address these kind of mm, discussions. Okay, so the main thing is once you do this, you succeed in breaking this, and then now you have basically all possible harmonics. Okay, of course, whether the magnitude now match with the data, that is still different story, right? But at least you have a scheme in which in your initial condition you have all these uh, harmonics to be non-zero to start with. Okay, so once you do this, now you see this is Vn and this is psi n, because all such symmetries are gone. So we should have both cosine as well as sine terms, which we have taken together and written in this way. And now even odd ends are can be present. Okay. So once you have this, you could have various different type of um, initial asymmetries, right? For I mean, here we had already seen the n equal to 2 even asymmetry, okay, which was this elliptic eccentricity. But now when you have the fluctuating nucleon positions, what I mentioned is that you start generating odd harmonics. And here we have given two examples of these odd harmonics. For example, you can have a dipole asymmetry in the initial state. You can have a triangular asymmetry in the initial state. So the dipole asymmetry here is shown in this cartoon, where this one represents like the center of mass, okay, of the energy deposited, right? And that is shifted in this way, and hence you can think like here there is more. So this, so outside you see this is vacuum, right? Whereas this, so the red contour here represents the overlap region, okay, and this one is say the point of highest entropy deposition. So when it is thermalized, this is the point where the pressure is highest, okay, and outside let's say pressure is 0. Okay, so this here you see the the gradient in the pressure, okay, is largest, right? Because this is the shortest distance and this is the longest distance, right? So the gradient in this right direction is larger, right? Gradient larger, and on this side the gradient is smaller, right? Because the same change in pressure is happening over a smaller distance compared to over a larger distance, right? So what will happen is when it now starts expanding, right, there will be a net kind of flow on to the right, right? So this is at the end, if this survives till the freeze out, okay, what you will see is a V1. The cosine phi will not be 0, the average of cosine phi, and so that coefficient is just n equal to 1 V1, right, at freeze out. Similarly, you can have these triangular kind of, so this overlap here, right, when you do a Fourier decomposition, you can pick out a n equal to 1 contribution, you can pick out a n equal to 3 contribution, right? And so in the end, if you superpose all these things, you should get back that, right? So even though we are drawing like this, huh, you should not think that the fireball is actually like the fireball is this, okay? It's some arbitrary shape, right? And this is just a decomposition into some well-known basis, right? And so similarly here you have, these are the short distances, right? So the flow, when it expands, the medium uh, flows preferably in these directions more, right, than these directions, right? Because these are the larger distance thing. So the gradient is smaller along these dotted directions than along these solid line directions, right? So and that's how you, in the end, you can get a V3 kind of a triangular flow. Okay, so exactly, now coming to the point which Devashish raised. So that is the initial geometry, right? But that is not all. Okay. Um, uh, in this course, of course, we are not getting into the hydrodynamics, which is a model to evolve these kind of initial geometry, initial conditions to the freeze out, right? Uh, what you will see that typically in a evolution model, okay, if it is a hydrodynamic kind of model, then in terms of these transport coefficients like shear and bulk viscosities, if it is a microscopic transport kind of model, where instead of evolving hydrodynamic field variables like energy, pressure, fluid velocity, that means you're talking of some macroscopic uh, variables, right? Not microscopic variables. But instead of that, if you are doing a transport evolution where you are talking in terms of how the partons are scattering with each other and they are expanding, right? So there, the parton cross section is a relevant thing to talk about, and that, in some sense, controls this macroscopic transport coefficient. So, so in a hydrodynamic framework, in terms of shear viscosity or bulk viscosity, and at the same time in a microscopic transport approach in terms of those parton cross section, those cross section or these transport coefficients, they can be tuned. And what you can see that, what you could see then, is that for the same initial geometry, okay, when you are varying these transport coefficients or say parton cross sections, you are actually playing with the medium transport property. Okay, of course, in nature it's some unique value, whatever QCD is, right? But one thing we didn't get a chance to talk in these lectures was that although lattice QCD, this first principle framework, is very much suitable to um, compute, or has been so far very successful in computing the equilibrium thermodynamic properties, the other kind of properties, medium properties, that you can also talk of are these transport coefficients, right? Means if the medium, instead of being completely in equilibrium, if we have a small gradient, right, then it will evoke a response from the medium, right? Some kind of transport of conserved charges, right? Either energy momentum tensor, and for that the relevant transport coefficients are these shear, bulk, and so on, or say some net baryon charge or electric charge, right? For which you have the corresponding transport coefficients like baryon conductivity or electric charge conductivity and so on, right? These transport coefficients, by first principle, in principle, they can be computed on the lattice. However, at the in the currently, those computations are not still in the level of the thermodynamic equilibrium quantities which we have already spoken of. So there is, I mean, there is a lot of progress that is happening, but to get a numbers which we can then put in the model and directly calculate, directly evolve, that day is still to come. We are still some time away um, from that. So currently we have to play around with these transport coefficients, or say these cross sections, and try to see what sort of phenomenologically inspired or motivated guess or parameterization that works best to fit the data. Okay, that's the game currently that is going on. Not so with the equation of state, right? The equation of state, say energy on pressure, uh, um, on baryon density. This thing is well fixed by lattice QCD. However, the transport coefficients, as I said, the lattice is still in a stage where it is not completely, like the final statement is yet to come. So the model people, they have a freedom to play around with these, to try to, and then hence from data. So it's the other way around. From data, you try to extract which kind of parameterization will works the best. So what describes QCD in these conditions the best? So to explain these phase space differential observables like flow at freeze out, one needs to model the evolution of the fireball with appropriate initial conditions where these symmetries are broken, and then that is not enough. You also have to choose appropriate medium transport properties like shear, bulk viscosities, etc., that control the magnitude of these flow coefficients, right? So, so when you try to compare these phase space differential observables with model, you learn about initial conditions as well as medium properties through such phase space differential observables. Okay, so more on this, of course, is going to be covered by Victor in his lectures on the hydrodynamics. So I have not planned any more um, slides. If there are questions we could take, I have just kept two empty slide to write things if there are questions or something else. Okay, thank you. So there are questions?
Sandeep,
Yeah,
can I ask one?
yeah, sure.
So as you as you have said that this V3 and higher order for flow harmonics or the odd flow harmonics, they are generated because of these fluctuating initial conditions, the fluctuations in the position of the nucleon themselves inside the nucleus. So
Right.
now, so smaller will be the size of the nucleus, so smaller will be the number of nucleons. So does that mean that there will be higher fluctuations in their position? Because if it goes as 1 by square root of n, so then if we have a smaller, do we expect a smaller value of Vn or V3 or V1 for a smaller nuclei?
Yeah, so this is so this is indeed also, you see, also can be seen from this kind of a centrality dependence, right? Here you have the largest firewall size, let's say, and then progressively it kind of becoming smaller and smaller. And we also, of course, in this scale, it is dominated by V2, so we are unable to see this nicely. But if, for example, if you had just plotted V3, you would have clearly seen that what you are saying is indeed true, that as you go to central to mid-central collisions, there is a rise in this V3, for example, these odd harmonics, all these higher order harmonics, in fact. Of course, in the end, there is this fall, but this is telling that it is the collectivity itself is breaking down. Yeah.
Because of your scatterings are smaller as you go to the extreme peripheral.
Yeah. Also, I mean, even in a hydro, so okay, maybe I should take back the collectivity breaking down, because you see, even the hydro is predicting it is falling. So why in the hydro it is predicting that although you see the E2, if you think the eccentricity, it is actually growing up, right? The ellipticity is growing up, but still the hydro says that you get smaller thing, and that because the central pressure right here is much smaller. So you need a shape, but you also need a strong core, because the gradient in pressure, right, this also needs to be large, right?
Yeah, so the degree
Yeah,
of harmonization itself will be smaller for extremely peripheral system because you do not have
yeah, so this gradient will be yeah,
establish the.
yes.
Oh,
Yeah.
thank you.
So indeed, when you when we do system size, there is this complication. So of course nucleons are reducing, but at the same time the thermalization degree is also changing. So there are a couple of factors which can interplay. Yeah, but indeed, at least up to here, if we think that thermalization is similar, then we can tell that yes, because it is decreasing nucleons, so this is increasing. Okay, good. So are there other questions?